All right, thanks, Gerge. Thanks everyone for joining us. We're really delighted to have here Adithya, Devraj, uh, joining us to give this talk. He's currently a postdoc. He moved to Stanford and he's working with Ben Monroy there. And previously he was a PhD student with Sean, who is a co-author on this paper. And he's been working a lot on making RL more efficient, dealing with the high variance of RL, and this talk is one outcome of this series of works that he was doing. So Aditya, take it away.
Thanks a lot, Chaba, and also thanks to Kiara and Garge for organizing this wonderful seminar series. So today I'll be talking on this our paper on Q-learning with uniformly bounded variance, which is a joint work with some of my wonderful collaborators, Shuhang and Shan at University of Florida and Anna Bieshecz at India. So before I start, I want to thank all the funding agencies for sponsoring my research, ARO, NSF, and UFII, and also a special thanks to ARO for also sponsoring my postdoc at Stanford. Um, so the motivation for this research is this kind of a bound on the error sequence that has been very popular in recent theoretical reinforcement learning papers. So here, theta n is the parameter vector that is the output of your reinforcement learning algorithm, Q-learning or TD learning, that is trying to approximate your Q function or your value function. Theta star is the optimal parameter vector that approximates one of these two functions. Gamma is a discount factor. P is a scalar that is usually bigger than or equal to 2. And B is some scalar quantity that depends on your environment parameters, and n is a number of iterations. Okay, so a lot of these reinforcement learning papers, they focus on efficient exploration techniques that tries to make this scalar b as small as possible. But I just want to clarify in the beginning that our focus is not on this clever exploration techniques. So the focus of this work is going to be on this factor, which is like a polynomial and this 1 over 1 minus a discount factor, and see if we can somehow try to make this better. Okay. So here is an example in multiple papers where such a factor appears. So it has been a dream for Shan since, I don't know, 10, 15 years, I think, that this dependency on a bound like this is very artificial in the sense that we may be able to somehow get rid of it. And he's been telling this for me almost since I started PhD with him. And finally, like after I finished my thesis, we recently got time to look at this issue. And spoiler alert, it turns out that this factor over here is due to estimating a constant that you ultimately may not ever care about. Um, and there were multiple directions in which we were looking at to kind of like resolve this issue. But the most elegant way of resolving this issue came about by looking at this paper by Abunadi, Bertsikis, and Borker on average cost Q learning. And I'll show you how these two techniques are essentially related. Okay. So here's the basic overview of the talk. So in the interest of the broad background of the audience, first I'll be formulating this Q-learning problem as a more general problem of stochastic approximation. And then I'll be looking at um, convergence and convergence rate of stochastic approximation algorithms. And then I'll be discussing how we can use this theory of stochastic approximation to characterize the convergence and convergence rate of Q-learning. And finally, I'll be introducing the relative Q-learning algorithm, and I'll be concluding with some direction for future work. So I'll be spending about like roughly 10 minutes on each of the first 4 topics here. So just in case you want to get distracted in between. Yeah. So first, the problem setup will denote X to be the stationary controlled Markov chain, and will denote U to be the input sequence or the control sequence or the action sequence, whatever you want to call it. And we'll assume that both of these sequences are evolving on a finite state and action space. We'll denote PU to be the transition probability matrix condition on the current action being U. That is, given the current state is X and you take an action U, the probability of ending up in state X prime is given by PU of X prime. We'll denote C to be the cost function that maps from state action pairs to a real number. And we'll denote gamma to be the discount factor. So given a deterministic policy phi that maps from state to action, so this can be randomized too, but I won't get into the details for simplicity. So the Q function for a given policy phi is defined to be this infinite summation of discounted cost. And the optimal Q function Q star is the minimum over all possible policies phi of this Q phi of X comma U. And we know that this optimal Q function Q star solves this nonlinear fixed point equation, which is known as the Bellman equation. So here I'm denoting T to be the Bellman operator that is defined here. And I'll also be using this Q underscore operator notation to denote the minimum over all possible actions. Okay. So the goal in dynamic programming is to find this function Q star that solves this nonlinear Bellman equation. Okay, so to find Q star that is satisfies Q star is equal to TQ star. One way of looking at this fixed point equation is suppose you choose an input sequence UN that explores each and every possible state action pair X and U, and you find a Q star that solves this conditional expectation equal to 0. So Fn is everything that you have seen up to time step n. And if you find a Q star that solves this conditional expectation equal to 0, then the solution Q star is the same as the solution Q star to this fixed point equation over here. So the reason for looking at something like this is you can think of Q learning, the goal in Q learning, as an approximation to the goal in dynamic programming. So specifically, let's consider a parameterized family of functions Q theta. So I'm using theta to denote the parameter vector. The goal in Q learning is to find this optimal parameter vector theta star that solves this projected Bellman equation, wherein we have taken this term inside this conditional expectation without the conditioning and multiplied it with a d-dimensional random vector, which is popularly known as eligibility trace or eligibility vectors in the reinforcement learning literature. And the goal is to find theta star so that this expectation is equal to 0. A very popular example of this eligibility trace is you let zeta n to denote the gradient of this function q theta at theta is equal to theta star. And this is basically what you do in, for example, dqn, wherein you have a target network that defines this part of the q function over here, and an online network that defines the q function over here. And when you take the gradient of this Bellman error square, you essentially end up taking the gradient only with respect to the second Q function, and you get something like this. It becomes a root finding problem of this sort. Okay? So the Watkins Q learning or tabular Q learning is a very special case of what I just showed. So in Watkins Q learning, you have a linear parameterized family of function. So here the psi denotes the basis function. The zeta n, the eligibility trace, becomes the basis functions itself, like whatever I showed earlier. And this is just like the TD0 or Q0 learning algorithm. The number of basis functions is equal to the number of state action pairs itself, and each basis function is defined to be the indicator function whenever you visit a particular state action pair. In this case, in this special setting, you can rewrite this function f bar of theta star as this quantity over here. So here pi denotes the d by d diagonal matrix, wherein each component is the stationary distribution of this Markov chain XU. And if each of these quantities is strictly greater than 0, you can see that solving this equal to 0 is the same as solving for the goal in dynamic programming. Okay? And one nice interpretation of this Watkins Q-learning formulation is that you have a you can look at it as an off policy SARSA algorithm, wherein you have a randomized exploration policy, and the target policy is the optimal policy itself. So you're using UN just to explore the environment, and you're learning for the optimal policy over here. Okay? And basically, you end up learning the Q function for the optimal policy. Okay? Now, once you have look at a problem of this form over here, this actually belongs to a more general class of problems known as stochastic approximation, and I'll get into details about what stochastic approximation is and how we can use the theory from stochastic approximation to analyze Q-learning algorithms next. Yeah. So next, I'll be talking about stochastic approximation. The goal in stochastic approximation is simple. You have a parameterized family of functions f bar of theta, wherein for each theta, f bar of theta is an expectation. So here Wn is a random vector, and this expectation is with respect to the stationary distribution of this random vector. And the goal is to find theta star so that f bar of theta star is equal to 0. Yeah. The algorithm itself, it dates back to Robinson and Monroe in 1951. So what the algorithm does is each iteration n, instead of getting this value of f bar of theta n itself, you have a noisy evaluation of this function f bar of theta n in the form of f of theta n and Wn plus 1, and you recursively update the parameter vector in this fashion over here. We'll be assuming that this alpha n, which is a scalar quantity, which is also known as a step size quantity, to be decreasing in this form over here. So we'll let alpha n to be equal to g over n plus n naught, where g is a positive quantity and n naught is a non-negative quantity. And the way you analyze this algorithm, noisy algorithm over here, is to look at this deterministic ODE, and if theta star is the stationary point of this ODE, then you can show that that the limit point of this algorithm itself is also theta star, and I'll be making this more precise in the next slide. And again, the way you view this stochastic approximation algorithm itself is to view it as a noisy Euler discretization of this deterministic ODE. So I'm rewriting this algorithm here as the mean plus this noise sequence here, which is basically equal to the noisy function minus its mean. So it has 0 mean. In tabular Q-learning, you can show that this is a martingale difference sequence. But I just want to clarify that in this section of stochastic approximation, the results I'll be showing does not need this assumption, which makes it more applicable in more general settings. So when it comes to stability and convergence analysis of stochastic approximation algorithms, there are two key results that I think are super useful. One is establishing convergence assuming boundedness. So suppose you have some proof that you can show that the parameter estimates are bounded sequence. And you can show that this ODE is globally asymptotically stable with unique equilibrium theta star. Then there's a theorem that you can use to show that theta n converges to theta star with probability 1. Yeah. And there's another result, which is slightly more recent compared to this previous result. What Borker and Main in this 2000 paper showed is that if you look at the ODE of this scaled function f bar infinity of theta, then you can, if this ODE is globally asymptotically stable, you can also get boundedness of this parameter estimate. Yeah. So basically, all you have to do to establish convergence of stochastic approximation algorithm is to establish the stability of these two ODEs, and then you're done. And quickly, how this applies to Q-learning is in this following form. So for Q-learning, what you have to show is the global asymptotic stability of this ODE over here. Again, recall that T is the dynamic programming operator, and the fact that this dynamic programming operator is a gamma contraction where gamma is a discount factor will establish the stability of this ODE. So if it is bounded, then the algorithm converges. And similarly, to establish boundedness, you need to look at the same ODE, except with the cost function equal to 0. And this cost function is something that appears in this dynamic programming operator. So basically, just by very simple arguments, you can show that the Q-learning algorithm converges just by looking at these two ODEs. Okay. But the focus of this talk is not on convergence of reinforcement learning algorithms. It's on the convergence rate. For that, I'll define the performance criteria over here. So let's denote theta tilde n to be the error sequence. That is, after n iterations, how far away are we from the optimal parameter vector theta star? The performance criteria in this talk is going to be this something known as the asymptotic covariance, which is defined to be this limit over here. And what this says is if this quantity here is finite, then you can get 1 over n convergence rate of this error sequence, mean square error sequence with the scalar being the sigma infinity theta itself. And this asymptotic covariance matrix is something that appears in also this limit theorem, so central limit theorem, and the law of related logarithms. For example, what the CLT says is for n large enough, this scaled error sequence is distributed according to a Gaussian with mean 0 and this variance sigma infinity theta, which is defined in this limit over here. So what the asymptotic variance theory for stochastic approximation says is the following. Let's denote sigma delta to be the error covariance matrix. So recall this delta n is the noise sequence that appears in your stochastic approximation algorithm. And let's denote A to be the linearization matrix at theta star. What the asymptotic variance theory says is if all the eigenvalues of this matrix G have real parts that is strictly smaller than minus half, then this quantity over here can be obtained as a solution to this Lyapunov equation over here. So recall G is the scalar that scales your step size. And if there exists at least one eigenvalue of this matrix GA that is bigger than or equal to minus half, then you can show that typically this asymptotic covariance is infinity. And what that means is the convergence rate is like slower than 1 over n. Okay.
Quick question,
Yeah.
Adithya. Where is the 1/2 plus 1/2 identity come from?
It comes from Taylor series for square root of n. So when you try to obtain a recursion for this sort of a quantity, so what you do is you look at the stochastic approximation algorithm over here, multiply the left-hand side and the right-hand side by square root of n plus 1. And on the right-hand side, when you do Taylor series for square root of n plus 1 in the form of square root of n, you get a half there. Yeah. And that's something that, okay. And I don't know what it really more philosophically means, but this is the mathematical reason for its appearance.
Right, and I also have a question here. I'm sort of lost, so can you remind me of the definition of G?
Yeah, so G is alpha n is G over n.
Oh, I see.
Yeah.
Gotcha.
Yeah.
All right, cool. Yeah, sorry about that.
Yeah, no problem. Yeah, any clarification questions, please feel free to stop me. Okay, so okay, so one might ask, like, why this asymptotic covariance? Like, why look at something that is like asymptotic in nature, and why not something that's more, like finite and bound? So I'll try to make a case here. So firstly, this eigenvalue test that I just showed is very easy to look at, and it's actually very simple. So all you have to do is look at this eigenvalues of this matrix GA. Again, A is this linearization matrix. And just for the optimization people in the audience, A is like the negative of the Hessian. Okay. So if all these eigenvalues of this matrix GA have real parts that is strictly smaller than minus half, then you can just show that this is finite and it is given by as a solution to the Lyapunov equation. Otherwise, the convergence rate is lower than 1 over n. So it's a very easy and simple test. Secondly, the theory extends of this asymptotic covariance. It extends to much more complicated settings where Hafting-style bounds do not extend. Okay, and one very simple example is in queuing theory, wherein you want to estimate the steady-state mean of a stable reflected random walk. And even in this very simple case, it's like very difficult to get a Hafting-style finite end bound. Yeah. But this again, this asymptotic theory, it extends to like much more general settings, which makes it maybe like likely more applicable in, for example, Q-learning with function approximation, and wherein there's noises Markovian and all that. But for our purposes, the reason like we like asymptotic variance theory is that it provides a useful tool for efficient algorithm design. So our goal is not really to get like good performance bounds. Our goal is really to come up with like good algorithms that that perform well in practice. And I'm like, so far for me, it has like the asymptotic variance theory has helped a lot in trying to come up with good algorithms. And lastly, what I want to say is we should use this asymptotic variance theory as at least a litmus test, wherein you can like immediately discard algorithms that really do not have good asymptotic convergence, right? Then there is no real, I guess, maybe in some problems there is, but in most cases there may not be any point in looking at the finite and bounds. So we can make this asymptotic. We can also make this asymptotic variance theory like much more precise for the case where this function f is linear. So for a linear stochastic approximation recursion of this form, where this function f is linear in this parameter vector theta. So an plus 1 and bn plus 1 are d by d random matrices and a d cross 1 random vector. We have the following recent result. So even if this matrix an plus 1 and bn plus 1 are functions of a Markov chain, what you can show is if all the eigenvalues of this matrix GA are strictly smaller than minus half, then this error covariance matrix can be shown to go to 0 as 1 over n, with the quantity being the asymptotic covariance and plus some higher order terms. And we also have a very nice negative result stating that if there exists an eigenvalue of this matrix GA that has a real part that is like bigger than minus half, less than by beta, then you can show that the convergence rate to 0 is at a rate no faster than 1 over n to the times 2 beta. Okay, and again, just to give you a context, in reinforcement learning, this quantity beta is like 1 minus gamma, or rather minus of 1 minus gamma. And it's if for large discount factor, it can be arbitrarily close to 0, and you can imagine like how slow this convergence rate can be. And you can optimize this quantity asymptotic covariance using various algorithms, and examples here are like Rupert's stochastic Newton-Raphson. This LSTD lambda algorithm is also a special case of is an algorithm that tries to optimize the asymptotic covariance, but that is not really their goal in the paper. And all these app algorithms are also designed to achieve optimal asymptotic covariance. Okay. So one last slide on stochastic approximation before I move back to reinforcement learning. So what I want to discuss here is something known as matrix gain stochastic approximation. So let's choose alpha n to be just 1 over n, and let's introduce a d by d matrix gain sequence Gn. So what I mean by that is you have a step size of this form, alpha n plus 1, Gn plus 1 over here. Let's assume that this sequence Gn converges to some matrix G. Then this is equivalent to looking at a matrix step size algorithm where the the step size is like G over n. So what the asymptotic variance theory says is that now you have to look at the eigenvalues of this matrix G times A, and you can make the same claims as before. If all the eigenvalues are strictly smaller than minus half, then the corresponding asymptotic covariance is given as a solution to this Lyapunov equation.
Can I have a quick question here?
Yeah.
So yeah, I'm wondering about this these asymptotics. Like it's really like strongly showing. I mean, like its strength is being shown here, right? Like because you're not assuming any rate at which Gn would converge to G, and yet you have this result. Is that?
No, that's not true. We need to ask. Yeah, Gn definitely needs to converge to G at
1 over root n. Is
yeah,
that
1 over n.
Is that right?
Yeah, I'm not too sure about that because because in for example in ZAP it doesn't converge at like 1 over n. So Gn is trying to approximate the Hessian in ZAP, and
I can imagine that there is no rate condition on here.
Yeah, I think maybe you have to. I think a good reference for this is Konda's thesis, and they have he establishes convergence rate of for at least for the linear 2 times scale stochastic approximation theory, for example.
And so there is also a question from Joel. He's asking whether Gn can be dependent on all the other data on the past.
Yeah, so it can depend on so it can depend on this random vector wn. For it to depend on theta n, you need like a little bit more assumptions, and you need to like deal with it. It's slightly more difficult to deal with it if it depends on theta n too. But yes, like you can make it a function of theta n, but it requires some sort of special case dealing to look at that. Yeah.
You're getting into the middle of this. Okay.
Yeah. Yeah, so I'll show you one simple example where this G is like in Q-learning, at least it makes a lot of sense. And another example is ZAP. So, yeah, so this yeah, like you said, this shows the real, I guess, use of this asymptotic covariance theory and how we can optimize algorithms. And that's exactly what I was going to get to next. So you can optimize this quantity here, this sigma infinity G over all possible matrices G. And it turns out that the optimal G is G star to be minus A inverse, which is what you would do in a Newton-Raphson like algorithm. And you can show that the asymptotic covariance theory, asymptotic variance for G star to be equal to minus A inverse, it can actually get it in closed form defined here. And you can show that it's smaller than or equal to the variance for any other matrix gain G, and in the positive definite sense. Okay. So again, an example of this sort of an algorithm that uses this matrix gain is LSTD lambda. Like you can show that LSTD lambda algorithm is essentially doing something like this, but it's doing it all at once instead of recursively doing it. And a lot of papers in stochastic approximation theory have been looking at something like this, since the Robinson-Monroe algorithm and also ZAP learning algorithm is also an example that tries to imitate this Newton-Raphson behavior. Yeah. Yeah, so now I'm done with the stochastic approximation theory. So next what we'll be doing is we'll be applying the stochastic approximation theory to Q-learning. So the picture on the left is of Vivek Borkar, who has done a lot of research in stochastic approximation, and here is trying to pretend to be a bandit. And on the right is Christopher Watkins, who basically invented the Q-learning algorithm. So again, recalling the goal in Watkins Q-learning is to solve this projected Bellman equation to be equal to 0. And the Q-learning algorithm itself is a direct application of stochastic approximation. So you take the term inside this expectation at each iteration, and you have a noisy evaluation of this function, and then you update the parameter estimate in this fashion over here. So this may not look very familiar to a lot of people, but if you replace this basis function psi with indicator function, then you can show that this is exactly the same as the Q-learning algorithm that looks more familiar. It is given by this recursion over here. So first, let's look at the case wherein the step size alpha n is defined to be like 1 over n. Just for simplicity. In this case, the linearization matrix A is defined to be this quantity over here. So where recall that this pi is a d by d diagonal matrix that contains the stationary probability of each state action pair. And P phi star is the transition probability matrix for this Markov chain XU with the policy being fixed to phi star. Okay, which is the optimal policy. What we can do is we can use Perron-Frobenius theory to show that the eigenvalue with the largest real part is lower bounded by this quantity over here, where again this pi is the maximum is over all stationary distributions of this Markov chain XU, and this is clearly bigger than or equal to minus of 1 minus this is like the largest value this can take is like 1, and because of that you can show that if whenever this discount factor gamma is bigger than half, then this quantity on the right hand side is bigger than minus half, and because of that, you can show that the asymptotic covariance is infinity whenever the discount factor gamma is bigger than half. So this implies that the convergence rate is slower than 1 over n if you use a step size of this form because asymptotic covariance is infinity. Okay, so we can use the negative result that I showed. Yeah, is there a question?
Oh, well, I'm just curious whether you can just set a smaller step size and resolve this, like set g equals 1/2 and you're done. No?
No, G, you want it to be like inverse of this. Yeah, you want it to be half times inverse of this whole thing, you know? Yeah.
Right.
Yeah, and I'll come to that like in next
Okay.
slide. Yeah.
Okay.
So you want actually you want G to scale like 1 by 1 minus the discount factor to really get anything finite asymptotic covariance, and that's something that I'll discuss in the next slide.
Okay. Okay.
Yeah.
Thank you.
Yeah. So like using the negative result that I showed earlier, we can show that this asymptotic mean square error convergence rate is slower than this over here, 1 over n times 2 times 1 minus gamma. And you can imagine if this discount factor is arbitrarily close to 1, this can be like very slow. And this is the kind of result that you can see, for example, in Chaba's paper, like on asymptotic convergence rate for learning. Okay. So that is not super interesting to us. That's kind of a step size. So what is much more commonly used in practice is a step size that looks like this. So here, n of x comma u is the number of times you have visited a particular state action pair x and u. And this is something that is like quite common in like Q-learning papers. So you can show that this kind of a step size is actually equivalent to a matrix gain stochastic approximation algorithm with G equal to pi inverse. Okay, and the step size alpha n is equal to 1 over n. So these two things are essentially equivalent, and this is something you can show very easily. And in this case, you get what you expect. the linearization matrix A is the same as before, except that you have gotten rid of this pi you had before using this pi inverse. Okay. And in this case, you have an exact value for this eigenvalue with the largest real part, and it is defined to be this minus of 1 minus the discount factor gamma here. And we also know what the eigenvector is, right eigenvector is, and it is all ones. And I'll come to like why this is useful in a bit. And once again, if the discount factor gamma is bigger than half, then asymptotic covariance is infinity, because all the there exists an eigenvalue that is bigger than minus half, and asymptotic mean square convergence rate is again the same whenever the discount factor gamma is bigger than half. But as Gerge just suggested, you can scale the step size. You can use a G that looks like 1 minus gamma inverse, and you can scale this quantity over here to get a 1 over n convergence rate, because the maximum eigenvalue then becomes -1 if you use this kind of step size. Yeah. As long as it is like strictly bigger than half times this quantity, 1 minus gamma inverse, then you can get 1 over n convergence rate. Okay, but there are reasons to use like exactly not multiplied by something like slightly bigger than half and multiplied by something exactly like 1. So yeah, again, so if you use a step size of this form, then you get like 1 over n convergence rate. But what happens is asymptotic covariance, it scales as like 1 minus the discount factor power -2, and that is something that you can get by looking at the Lyapunov equation over here. And this is something that you kind of expect by looking at these finite time bounds that has a factor that blows up as 1 over 1 minus the discount factor power 2 or whatever. Okay, so we recovered an expected result here. So now I'll be introducing the relative Q-learning algorithm. So the goal in Q-learning is to solve this nonlinear fixed point equation. So again, T is the Bellman operator, which is defined here. The goal in relative Q-learning is to solve a modified nonlinear fixed point equation. So let's call that relative Bellman equation. So here T tilde denotes the relative Bellman operator, which is the same as the Bellman operator, except that you're subtracting off a constant over here. So here delta denotes a scalar that is positive scalar, and mu is a PMF on the number of state action pairs, and this inner product will denote the expectation of H star with respect to mu. Okay. And let's say you solve this modified fixed point equation instead of this fixed point equation here. There's actually a direct relationship between the solution to this relative Bellman equation and the solution to the Bellman equation in this form over here. So you see that the Q function is equal to the relative Q function plus some constant that basically blows up as the discount factor gamma is arbitrarily close to 1. So a very important thing to notice here is that let's say you're interested only in the optimal policy, which is the minimizer of this function Q star. You notice that this constant here is irrelevant to obtain the optimal policy. So the minimizer for this function Q star is the same as the minimizer for this function H star, because the constant is something that is added to each and every state action pair. Okay. Now we can get an algorithm or the relative Q-learning algorithm here by directly applying the stochastic approximation theory to solve this fixed point equation over here, and it is something that looks like this. And again, for the tabular case, it looks like in a something more familiar form over here, where you have like an update rule that looks very similar to the Q-learning update rule, except that you're subtracting off a constant over here. To establish stability and convergence of an algorithm, firstly, this recursion, it looks very similar to the average cost Q-learning algorithm of this paper by Abunadi, Burtsikis, and Borkar, and we can use very similar techniques to establish stability and convergence of this algorithm here. But because we have an additional discount factor here, which they don't have, we can also, the proof is like slightly more simpler, and the key is using the fact that the relative Bellman operator is actually a gamma contraction in the span semi-norm and not in the L infinity contraction, not in the L infinity norm because of this constant. Okay? And then you need to separately deal with the constant and show that even that goes to 0. Okay? But again, the focus is not on the convergence. So what we're really interested in is the convergence rate. So let's do the eigenvalue test for the relative Q-learning algorithm. So this is the linearization matrix for the relative Q-learning algorithm. So it's the same as that for the Q-learning algorithm, except there is a constant or a rank 1 matrix over here. So it turns out that the eigenvalue corresponding to the right eigenvector 1 is actually minus of 1 minus gamma plus delta. So you can see that by just multiplying the right-hand side by all ones, and using the fact that this P phase star is a stochastic matrix. You can also show that all the other eigenvalues of this matrix A are strictly smaller than or equal to minus of 1 minus gamma rho star, where rho star is the maximum where rho star is the real part of the eigenvalue with the maximum real part of this matrix P phase star. Okay. So because P phi star has an eigenvalue 1, you're not including that because of you're getting rid of that over here. You can use the same theory I just showed before to show that if you use a step size of this form now, so it's the same as the one you use for Q-learning, except that you have to scale it by 1 minus rho star times gamma to the power minus 1. Then you can show that the algorithm achieves finite asymptotic variance. And I need to just clarify that this, under very general conditions, this rho star is smaller than 1. And one example is when this P phase star is the transition probability matrix for a unichain Markov chain. Using this kind of a step size, what we find is that the asymptotic covariance of the relative Q-learning algorithm is proportional to 1 minus rho star times gamma power minus 2, and instead of 1 minus gamma power minus 2. And this is again something you can establish by looking at solving this kind of Lyapunov equation.
So wait a second, Adithya. So this must come with some conditions on delta, right?
Yeah, so delta needs to be bigger than, you need to make delta big enough so that, okay, you can just make delta equal to gamma, for example, and then you have the eigenvalue corresponding to right eigenvector is minus 1.
Okay.
So anything that is like smaller than, making this smaller than minus half is good. But just to be safe, you want to put it at minus 1.
So putting it as like 1 minus gamma is a bad idea?
1 minus gamma is a horrible idea. So the thing is, if delta equal to 0, which is what happens in Q-learning, okay, then this eigenvalue becomes minus of 1 minus gamma. Okay, and then the largest eigenvalue with the largest real part of this matrix A will be equal to minus of 1 minus gamma. And and you need to use a step size of, again, 1 over 1 minus gamma kind to get rid of, to scale it back to something that's like smaller than minus half.
Okay.
So basically what we're doing here is we're making this, the problematic eigenvalue at minus of 1 minus gamma kind of irrelevant by adding this delta here.
I see. No, I'm just asking because this matrix reminds me an awful lot to the fundamental matrix that you see in infinite horizon problems, where you set delta as 1 minus gamma and mu you set as the stationary distribution of the chain. So maybe that's going to pop up later.
Oh, yeah, I think no, delta to be equal to 1 minus gamma. Yeah, I think that's
yeah, and mu, but mu needs to be the stationary distribution for that to make sense.
Yeah. So yeah, Yeah, mu can be the stationary distribution. That's fine, but I don't think delta to be equal to 1 minus gamma is a good idea. Because then it's too small. You want it to be like big enough.
Oh, I see.
Yeah.
Well, I guess we can get back to this later.
Yeah.
Yeah. Because you have some important things to say. Yeah.
Yeah.
Right.
Yeah. I'm almost done. Yeah.
Right. Please go ahead.
Yeah. So here's basically what we're doing. Here's the eigenvalues of this transition probability matrix PC star. So you have one eigenvalue at 1, and then all the other eigenvalues can be, there may be other eigenvalues on this unit disk, but its real part is strictly smaller than 1. The eigenvalues of this linearization matrix for the Q-learning algorithm is a scaled and shifted version of this over here. And you see that there's a problematic eigenvalue at -1 minus a discount factor. So basically what we're doing in this relative Q-learning algorithm is that we're taking this problematic eigenvalue and we're moving it within somewhere inside. Okay. Now the most problematic eigenvalue for this relative Q-learning algorithm becomes these two eigenvalues over here, which have the same real parts. Okay. That basically summarizes like the technique we're using here. Okay. So now how does this algorithm perform in practice? So as expected, we noticed that the relative Q-learning algorithm converges to 0 Bellman error like very fast. So what I have plotted here is the red is the Q-learning algorithm that has the same step size that is optimal for the relative Q-learning algorithm. The blue curve is the Q-learning algorithm, which is like the optimal step size. The yellow curve here is the relative Q-learning algorithm, which is with the optimal step size for it. And this is for discount factor to be 0.999, and discount factor is 0.9999 here. And you see that the variance like increases significantly for larger discount factors, but the relative Q-learning algorithm does not seems to be like kind of unaffected by the large discounting. Finally, a twist in the tail. So what we can show is like, again, by going back to the eigenvalues analysis of both the Q-learning and relative Q-learning algorithms. So what we just showed is that the eigenvalue corresponding to the right eigenvector 1 is this over here, and the eigenvalue corresponding to the right eigenvector 1 for the Q-learning algorithm is -1 minus gamma. And this is something we actually use in the proof of like the convergence rate of relative Q-learning algorithm. We can show that every other eigenvalue of these two matrices is actually exactly the same except these two. Okay. What this can be shown to imply is that for any vectors v and w that is orthogonal to this all ones vector, you can show this v dagger sigma infinity theta times w is the same for both these algorithms. So again, sigma infinity theta is the asymptotic covariance for each of the two algorithms, and we can show that this can be the same for both the algorithms, provided that you use the same step size for both the algorithms. Okay. So what this basically means is that the convergence rate of the two algorithms can be the same, again, if you use the same step size, except in the subspace corresponding to the constant basis function. So if you choose to ignore this constant, error in your constants, and if you use the same step size for both these algorithms, then the convergence rate of Q-learning and relative Q-learning algorithm in this subspace is actually, in the subspaces functions, is actually exactly the same. Okay, that's what this is saying. Okay. And now let's test like if that is true. Now what I'm plotting here is again the same three algorithms: Q-learning with its optimal step size, and the Q-learning with the step size that is optimal for the relative Q-learning algorithm, and the relative Q-learning algorithm with its optimal step size. And you notice that if what I'm plotting here is a span semi-norm of the error between the Q function and the optimal Q function, and we notice that the performance of relative Q-learning and Q-learning is exactly the same. Okay, and for both the discount factors, 0.999 and 0.99.
Quick
So
question.
what this is, yeah.
It just popped to mind that maybe the advantage function, like when people are learning the advantage function, it is trying to do something like that, because that's for the span too, right? Like then.
You mean in actor-critic algorithms? Yes, I think there is a connection.
Yeah.
Yeah, I think yeah, that is like one idea. Yes, essentially, there's a relationship between like trying to learn the advantage function instead of the Q function, and trying to learn the relative Q function over here. Yes, there is a very close connection between the two. Yeah, and I think it's like the same idea. Like it's then much more generally, this is like using the control variate techniques that has like been like quite popular. Yeah. So yeah, that's it. So you see that like if you use a step size that is like, so basically the point here is you should not use the step size like 1/1 minus the discount factor for Q learning, which people think is the optimal. And that is optimal if you are looking at convergence to the optimal Q function itself. But if you're really interested in like getting a policy and you can choose to ignore the constants, then essentially you can use a smaller step size and get better convergence rate. So in conclusion, stochastic approximation is still useful to design and analyze reinforcement learning algorithms, even though like a lot of people think it's like obsolete. But it seems that most complexity in classical Q learning seems to be spent on estimating this constant in this Q function, which you may not really care about because ultimately you may be just interested in this policy, and keeping everything relative, it doesn't really hurt us if you're interested in just getting the optimal policy. Yeah. The relative Q-learning algorithm, it results in an algorithm that has asymptotic variance that is uniformly bounded for all discount factors that is smaller than 1. It also directly gives us the Q function using that mapping that I showed earlier, but the question is, do we really need it? And maybe not if you're ultimately interested in just the policy. Okay. The algorithm can, of course, be zapped using the zap Q-learning techniques, and the asymptotic covariance corresponding to the relative Q-learning algorithm is defined to be this quantity over here, which can be like much smaller compared to the asymptotic covariance for the Q-learning, zap Q-learning, because of a better conditioned A matrix for the relative Q-learning algorithm. And I guess the next step is to basically establish this conjecture. We have an asymptotic result now. The next step would be to prove for each n such a bound holds, and that's the next work. And here are all the references that which this work was based on. And thank you.
Yeah, thank you.
Okay. Yeah, questions.
Yeah, very nice. So,
yeah.
Well, I don't know. I guess I have like a bunch of questions along the lines of the previous ones that I already asked, but I guess maybe let's give the floor to some other people.
Sure.
I guess you took note of a few questions.
So,
Kira, can you?
Alec had a question.
Oh yeah, please go ahead, Chava.
Alec, are you here? You had a question about the hashing of the projected Bellman.
Yeah. Hello, everyone. Can you hear me okay?
Yeah, it's good. Yeah, I can hear you.
Yeah. So yeah, very interesting work. I intuitively think that there is a connection between these matrix momentum methods and quasi-Newton algorithms. So I was wondering if you could comment about the relationship between asymptotic covariance as a way to quantify how good is an algorithm as compared with like the Hessian of the projected Bellman error, for example.
I didn't. So there were two questions related to matrix momentum and Hessian. I didn't. So yeah, sure, we can use matrix momentum techniques to get a matrix momentum relative Q-learning algorithm from this, and that will have the same asymptotic covariance as the zap algorithm. But we proved the results only for like linear case and all that stuff. But we can extend the algorithm. But I didn't understand your second part of your question, I think.
Yeah. So if you look at the asymptotic covariance of these algorithms, I think the reason that this works better is because it has a smaller asymptotic covariance.
Yes.
But this is somehow a second order characterization. So I'm just wondering, what is the relationship between this quantity and the Hessian of the projected Bellman error, or some other more standard numerical optimization?
Okay.
Second order fitness.
Okay, I think I get your question. So firstly, the Hessian in optimization is like the Jacobian in the problems that we are looking at. Okay. So this A matrix can be thought of as this linearization matrix. What I kept saying is like the negative of the Hessian itself. It's like you can basically apply the theory that I just discussed here directly to optimization, stochastic optimization problems, and here in that case, this A matrix would basically be equal to negative of the Hessian. But the issue is, again, like you're getting asymptotic convergence right here, but in stochastic optimization you have like all this like convexity and other things that can help you like try to get sort of better bounds, but which may or may not be possible in Q-learning, and in some cases it is, but more generally it may not be possible.
Yeah, that's true. For example, second order information really in the non-convex setting is only really helping you improve dependence on the condition number, for example.
Yeah.
So, you might observe some of those kinds of results in reinforcement learning as well. But yeah, anyway, okay, thanks.
Yeah, no problem, thanks.
All right, so there was another question by Ahmed Tuati. I don't know, Ahmed, can you ask a question?
Yes.
Right.
Sorry. Okay. Yeah. So my question was about the asymptotic variance. So when you saw the I think the Lyapunov equation, so you have one over identity involved in the equation. So I think if you take, for example, constant step size and you take Boolean averaging of the iterates, so this 1 over identity disappears in the equations, and also then you don't need to have this like the real part of your eigenvalues smaller than minus one half, but just non-positive.
Yeah,
so it relaxes a bit the condition of the convergence, I think.
Yeah, so you can definitely use Pollack-Rupert averaging for both the algorithms, Q-learning and relative Q-learning, and in each of those cases, what you would be getting is asymptotic covariance that looks like this, which is the same for ZAP. In our ZAP paper, we observed that Pollack-Rupert averaging, even though it has like the same asymptotic covariance as the ZAP Q-learning algorithm, it can be like have the very bad transients. But in any case, to answer your question, yeah, sure, we can I mean, get rid of this requirement of this big step size, but eventually the asymptotic covariance is still going to scale as 1 by 1 minus the discount factor, because this linearization matrix, even in that case, even if you use Pollack-Rupert averaging, will have an eigenvalue that is very close to 0, like in the form of -1 minus the discount factor. And you can use the Pollack-Rupert averaging for the relative Q-learning algorithm, and that will not have that issue.
Okay, I see. Actually, I have another question about the second part of the relative Q-learning. I think it's kind of known, like when you take like a value function is equal to the expected reward divided by 1 minus gamma plus a term that like h of s, which a function that converges to 0 when gamma goes to 1. I don't know if you are following. So actually, when gamma is equal like 10 to 1, like the first term, which is the expected reward divided by 1 minus gamma, this like goes to infinity, and actually this term doesn't discriminate between the policies because it's a constant term. And that's why actually I think when gammas goes to infinity to 1, we have this kind of instability, because like we are focusing a lot of effort to estimate this constant, but this constant is not relevant to the to solving the task. So I think like it would be nicer to estimate the h of s, like the relative value, and I think this is what you are trying to estimate, right? I'm not sure if this is like
yeah, that's exactly what we're trying to do. So I guess again, the point of this paper is like twofold. Even though we're looking at new algorithms, we were trying to resolve this issue in this bounds. So what essentially we're trying to say is, in these bounds, you have this dependency on 1 by 1 minus discount factor. What we're trying to say is that is a very artificial thing, and we don't really have to use big step sizes to get such a to get like a good policy ultimately is which is what you care about. And if you use a big step size, then what you said is not true, in the sense like if you use even though like basically if you use a big step size, then you can basically screw up the fact that even though you're looking for just the policy, you can get a very slow convergence rate, just like I showed over here, for example. So in this blue curve, but like, yeah, sure, you might argue that like in practice you might just do hyperparameter tuning and then find the best step size. Then I guess the point over here we're trying to make is in that case your bound should not depend on something like 1 by 1 minus the discount factor. Okay, it's more of a theoretical point of view.
Okay, I see. Thanks.
Yeah, no problem.
So I have a sort of similar question to this, which is about sort of the history of this idea of relative Q-learning or so. So like, how did you come up with this? Because it does resemble this relative value iteration algorithm a lot, where you would set delta and you would just pick like any fixed distribution mu, such that you just shift your value function after every update.
Yeah.
So this is the only thing that pops to my mind, but maybe you can tell me more.
Yeah, I think relative value iteration, I don't even know like how old that is. I mean, I found it in Putterman's book, and also I used a lot of the theory from there to develop this algorithm. And also I think when it comes to Q learning, the oldest work I know is, or the only work I know is by the paper that I showed earlier by Abunadi, Kotsikas, and Burkar. But I guess relative Q value iteration is something that probably is, you can find again in Putterman's book. But I think this is like very old. But again, the point here is like, I guess not the algorithm, it's more about the convergence rate. And then I guess showing that these bounds are very artificial, and you should not be looking at something like that. And maybe like it makes sense to kind of, change the objective itself in like this like Q-learning papers to look at something like the span semi-norm instead of like the L infinity norm, when you're really not caring about this constant.
Right, thank you. Well, I guess, just staring at this formula, I'm actually just realizing how silly my suggestion about delta was. I mean, you obviously have to set delta as something like gamma or so, and that's when you recover the fundamental matrix as delta as gamma goes to 1. All right, perfect. Thank you. So, any other questions?
Yeah, there was a question by Dhawal Gupta. Dhawal Gupta, are you with us? You were asking a question about relative matrix step sizes.
Yeah. Can you hear me?
Yeah.
So I'm a little new to the stochastic approximation thing, and I was trying to understand RMS prop and Adam for TD learning. And there are two ways through which I'm going about this. One is online convex optimization, and the other is stochastic approximation. In the second way, the G matrix that I get for the update is dependent upon the current and the past parameters as well, the past gradients. So I don't understand how the analysis will change for that. How should I modify the analysis for that? Or if that
how does it what?
So the G matrix is the moving average of the squared gradients, and we take a square root inverse of that diagonalized square root inverse of that as a matrix and multiply it to the current gradient.
Okay. Yeah. I don't know.
Yeah, you'd have to linearize more, right? Yeah. G can't depend on theta. You have to differentiate again, right?
G. Yeah, I don't understand the question, but
sorry, I can repeat that. The G doesn't depend upon theta; it depends upon the gradients or the data, past data as well.
Sure.
So at the updated time step t, my G contains the information from previous time steps
Sure.
also, and I'm not able to do that as a noise because I'm multiplying it by the current gradient.
Oh, okay. So then what you have to use is this two-time scale theory. So if you try and so the dependency, you can make sure that the dependency on the most recent parameter is bigger than the dependency on the past parameters. And then there is a two-time scale theory that says that you can basically replace this G to be a function of exactly the most recent parameter and like basically independent of the previous parameters. Maybe that will help you, I guess.
Okay.
Does that answer your question?
Yeah. Okay. That gets me my direction.
Okay.
Thanks.
Yeah, thanks.
Okay, so Roshan Sharif had a question. Roshan, can you ask a question?
Yeah, hi. So maybe this is more generally a question about learning policies generally rather than Q-learning. But so this constant that you're trying to learn is basically the average reward of the policy, right? And we don't really care about it in the discounted setting.
If mu was equal to pi, I think what you're saying is true, but we're not really trying to learn this constant. We're trying to ignore that constant. Yeah.
So my question is, so it's true that in the discounted setting, you don't care about that constant, but the constant is telling you something about the behavior of the policy performance as gamma is very large, right?
Yes.
So in the case where gamma is quite large, like larger than the mixing time of the MDP, do you think there's a point where it actually is better to learn this constant rather than just trying to reduce the dependence of one minus one?
Okay. First of all, I never said like learning this constant is useless. Like if you're interested in trying to learn the value function, like how good your policy is, then you definitely need that constant. Okay. So where it really becomes relevant is when you're looking at the policy. Like ultimately, if you're really interested in just the policy, then that constant is useless. Okay.
Right, but I meant if you're trying to evaluate the policy in the regime of gamma close to 1, then just sort of it might be more efficient to learn that constant. If it is so it takes on the order of the mixing time of the policy to learn that constant, right?
Yeah. So in that case, I guess what you could do is so if you really want to learn the constant too, and if you want to use this relative Q-learning algorithm, so you can learn this relative value function h star, and then there is a direct connection between a relationship between this Q function and this relative value function. You can just get it directly by just adding this constant over here. Okay,
right.
So and mu h star is something that you would have calculated recursively in your algorithm, or rather, like it's part of your algorithm itself, you can get this constant. You can just add it back. But so just to clarify, and if you add this constant again, and if you look at the error bounds between this transformed, or rather, like you try to look at the bounds between this Q function that you learn from this related Q function by adding this constant and the optimal Q function, you get back that 1 by 1 minus discount factor in your bound. So it basically, I mean, I don't know if it really nullifies the effect of relative Q learning, but you get back that factor for sure.
Okay, thank you.
Yeah, no problem.
All right. I think we do have a bunch of other things that we can discuss, but I think maybe we should just like call this the official end. and we can go to the offline phase so that people who want to leave, and they can leave. Okay. So thanks, Adithya, again.
Yeah, thank you.
Yeah.
Yeah, thank you.
I'm going to stop recording.